Hi! What unseen things will be revealed in this episode? Today we will dive into the world of four-dimensional electron microscopy. We will show how, thanks to a new method called 4D STEM in SEM, an ordinary scanning electron microscope can compete with much more expensive. Hello, my name is Martin, and these are the Unseen Talks. Today, I'm thrilled to welcome Associate Professor Miroslav Slouf, head of the Polymer Morphology Department at the Institute of Macromolecular Chemistry of the Czech Academy of Sciences. Hello, Mirek.
Hello, and thanks for inviting.
He is the author of a recent study showing how some clever tricks can transform a standard scanning microscope into an electron diffractometer. Welcome, Mirek, once more. And together with us is also Pavlína Sikorová, a PhD student at the Institute of Scientific Instruments in Brno, who collaborates with Mirek and adds artificial intelligence into the mix. Welcome, Pavlína.
Hi.
And finally, my colleague Pavel Stejskal, founder and CEO of Arvascope, the company that is developing hybrid pixel detectors and make this research even possible. Welcome, Pavel.
Hello.
Before we dive into details, please try to explain me in simple words, what are these 4 dimensions? Because as a simple man, for me, it's really confusing. I know just 3 dimensions. What are these 4 dimensions? What are we talking about?
So I suppose that this is a question to me, because we are one of the authors, me and Pavlína are one of the authors of 4D STEM. So basically, all images that we get from an SEM microscope or TM microscope are 2-dimensional images, X direction, Y direction, everything is fine.
Just a flat image.
Just a flat image, so 2-dimensional images. And if we use 4D STEM and pixelated detectors, then we have a set of 2-dimensional images for every single point on the microscope. Every single position of the electron beam is transformed in 2D image. So we have 2D image, which is composed of another set of 2D images, and 2 multiplied by 2 makes 4.
Okay, still I cannot imagine. Maybe some pictures will help me. Anyway, in your recent study published in Microscopy and Microanalysis, you presented results that are typically possible only with much more expensive transmission microscopes. But thanks to the pixel detectors, you made the same results in a standard scanning electron microscope. So what exactly did you show? Can you explain?
For this, we prepared a kind of simple introduction. At least we hope that it is simple. So what we have is 4-dimensional scanning transmission electron microscopy, as already mentioned. Each XY position of the scanning electron beam gives us 1 image, and so 2-dimensional array of 2-dimensional images gives us this 4D STEM. So let's have a look how it works. We have a very thin sample, typically with some crystalline specimen, and then we start scanning with scanning electron beam. The electron beam goes from the, let's say, upper left corner, goes point by point through the sample, and for every point we get 2-dimensional images. If the beam is quasi-parallel, then the image, due to some physics behind, is a nanobeam diffraction pattern. So for every single position, we would get a diffraction pattern. This is a simplified scheme.
Okay. This is the first 2D, and this is the second 2D. Right. Okay.
More or less like this. So we have this one from one corner, the other one from the second corner, and so on and so forth. From every position, we have a 2D image. In our case, nanobeam diffraction pattern, and the collection of the diffraction pattern makes the whole data set. It is usually very easy with modern detectors. This will be the next question, perhaps. With modern detectors, it is quite easy to collect such a huge data set, typically several gigabytes, even terabytes of data, but it is quite difficult to process it, if not for other reasons. Then the reason is that it is really huge and really big, so what to do with such a data? And our approach and the thing that you mentioned, how do we approach the problem. We said that for a common user this is impossible, so we would like to simplify the whole thing, and we reduce this complex 4-dimensional dataset to a single powder electron diffraction pattern. This is easy peasy. Even for average PhD student, the powder electron diffraction pattern after 2-hour training can be processed. So we greatly reduce the problem. We miss some information, but we give the user the possibility to deal with these huge data sets. So what can we do? We can sum all those diffraction patterns, hoping that we'll get the powder diffraction pattern, but alas, we fail, because if we sum our files due to inelastic scattering and other things behind the scenes, the diffraction pattern looks ugly. We can see no sharp rings. We can be more clever. We can filter the files because we have those single diffraction patterns. We can select only those with more diffractions and low background. Then it is much improved, but it is still not everything. We can do yet another mathematical trick. We can use the images in which we see only the central spot. If we do so, we can have a model of the primary beam. As we know, the final diffraction image is a convolution of the primary spot and the diffraction spot. So we can do the deconvolution. This is a costly operation, but if we do it, what we get are nice diffraction rings, and this is simple. From now on it starts to be simple. What we should emphasize is that all those things are done in our software programmed with the help of Pavlina, and so user gets this one, and this can be easily processed and used to identify the crystalline structure in your sample.
Okay, so what was originally supposed to make just an image of a surface is now revealing the crystalline structure.
Exactly.
Okay, this is something new. It was not possible until now.
It was quite easy, and it was readily available, but in TEM microscopes. Okay. So in TEM microscopes, this is standard method. In SEM microscope, this was virtually impossible. This is really the first possibility how to obtain simple diffraction pattern that can be processed by common user in an SEM microscope.
Mm-hmm. I guess, Pavlina, the software is the core of it. Of course, you get the images, some data, but the post-processing is the core of it, right?
Yeah, that's true. And just like Mirek said, the aim was to make it as simple as possible for the users, even for PhD students, which I happen to be one of them. And even though I'm not a microscopist or a crystallographer, I'm still able to operate it and produce these nice 2D diffraction patterns. So we are trying to.
And thank you. And hardware-wise, the enabler of it is the hybrid pixel detector, right, Pavel?
Correct.
Without it, why it would not work?
Because you're missing that second 2D set of information. So you need something like camera, which is, in this case, our hybrid pixelated detector.
Okay, we will talk more about it later. Now, I know we have also prepared some concrete results, because you have tested 6 different nanocrystal types. Their names I cannot even pronounce. However, what do we see here, Mirek?
Okay, so the first example are gold nanoislands. Gold nanoislands are small nanocrystals with very high diffracting power, and what we see here, this is the direct summation of all those nanobeam diffraction patterns. In this case, we see that even without any mathematical processing, we can see quite nice diffraction rings. When we do filtering, it is even better. With our deconvolution trick, it is yet better. But in principle, for perfect crystals like this, gold, very strong diffraction power, it works perfectly, and is quite comparable, even slightly better than in the case of standard TEM selected area electron diffraction. So in this case, really scanning electron microscope can compete and even overcome or even be better than TEM microscope.
So this black line, the dash one, is standard TEM.
Is standard TEM, and if we compare the signals, we can see that the best what we can get from our technique gives us sharper peaks and better resolution in the diffraction pattern in this case.
Okay.
Then we can go to more difficult crystals like terbium trifluoride, nanocrystalline aggregates. Why they are more difficult? Because as they are aggregates, there is more absorption, so less sharp diffraction rings. We do the same processing. If we just sum all those single nanobeam diffraction patterns, we get more or less nothing. Filtering helps us a bit, and deconvolution again can lead us to the results that are better than in TEM, as seen here, like in the previous image. This is the standard TEM method, and our peaks are even sharper. This is still not the end of the story. We can go even farther, and we can go to very challenging crystals for SEM microscope. Why? Because in TEM microscopes we have higher energy of electrons, so they go straight the sample even if the crystals are bigger and if there is high absorption. For SEM microscope, where the energies of the primary electrons are lower, this is more difficult, more challenging, more absorption, more inelastic scattering. To sum it up, if we do direct summation, we see just the primary spot and the noise. The same if we do filtering, it will not help us. If we do the deconvolution, it's much better. Not as nice as in the case of TEM, but still enough to identify the crystalline structure. And this is the thing that was not possible in SEM microscope previously, to identify the crystalline structures. This makes the SEM machines comparable to TEMs.
And I guess at the same time the TEM machines are much more costly.
Sure, because the typical TEM, I'm sorry, I cannot calculate in euros, but in Czech crowns it's around 10 million crowns, and this detector that you can add as an add-on device to SEM is around 1 million. So it is 10 times less, approximately. Maybe Pavel can give us a more precise answer.
Pavel, how difficult it is to upgrade an SEM electron microscope to provide these results?
Well, it's relatively very easy, because the only thing you need to do is just to put our detector, which comes basically as a front end, which goes into the chamber, and then the readout electronic sits outside of the chamber, and that's basically all you have to do with your current electron microscope.
Unseen Talks.
Well, if I understand it correctly, it essentially turns SEM microscope into something like TEM. Who could they get benefits of it in real applications or research? Who can use it? For who is it supposed to be?
If I can answer from the point of view of academia, definitely it would be interesting for any laboratory that is working with scanning electron microscopes, typically, such as geologists. They use a lot of scanning electron microscopy. They can do imaging, standard 2D imaging. They can do some spectroscopy like EDX spectra, and now they have the unique, they may have the unique opportunity to update the microscope so that they can see also diffraction, which is important to identify various minerals and so on and so forth. So for academia, it is definitely interesting and not so expensive. For industry, again, I think that Pavel is the better one to answer it, because I'm just a researcher, not from industry.
Where do you see the room in the industry?
Because one of the other applications is also for FIB-SEMs, which means the SEM that have the ion column as well. So you can prepare the lamella out of your sample and then directly visualize it in situ with your microscope, with your SEM, before possibly transferring to TEM. Because you have like the control of your quality of the lamella directly in the microscope where the lamella is created. So you can visualize many things with that. And then possibly if you want to do more of the analysis, then you know that your lamella is good, and then you transfer that sample into TEM.
So on more fundamental level, what kind of industries are these? So new materials or semiconductors or metallurgy, or what industries?
Yeah, mainly the semiconductor.
Why do they need it?
Because they create a lot of lamellas to visualize how the transistors look like in the nano details.
Oh, I understand. Thank you very much. Pavlina, you have the experience to work with it with your own hands. So how difficult was it for you to operate it?
Well, to be honest, like the acquisition of the data, I usually do it with my boss, Vladislav Křižánek. I'm mostly like sitting aside and helping with the helping it software-wise. But like from my point of view, the Advascope prepared everything perfectly, so we just we just ran the program that was made for the data acquisition, and it is collected. We get the data, and then we can do more with that. For example, the Fourier SEMPI and BD that Mirek was talking about.
Maybe some interruption. Sorry for that. This is the principle. The data collection, in principle, is easy. The hardware is ready. The trick is to process these huge data sets, and then as Pavlina confirmed, there's the data collection. Everyone can do this.
Yeah. Before we jump to the data processing, this image shows the implementation. Maybe Pavel, tell us what we see here.
Well, you can. If I may use your pointer, then. Here you see the pole piece of the electron column, so the electrons are coming from the top. Then you put the sample on this row bar holder, which is depicted here, and then you have like variety of detectors. This is a standard stem, which is just a segmented diode, and then our detector, our pixelated detector, is here in the bottom. So as you're scanning your beam over the sample, then you're collecting the data using this detector.
Yeah. Thank you. You mentioned, Mirek, that these are huge amounts of data. Isn't it slow in the end of the day?
The data collection is pretty fast. With the previous version of the detector, it was in minutes. Now it may be even in seconds. So the data collection is easy. The data processing is a different story. Our first algorithm worked. It was easy from the point of the user, because user just inserted the input data and ran the algorithm, but it took as much as 5 hours, maybe even more in extreme cases. And this is when Pavlina comes to play, because she managed to improve the speed much more. So maybe for you.
Yes,
how was it done?
Well, in principle, it's very easy, because when I came to the software, it's run serially. That means that like one picture at a time, but computers, thankfully nowadays, they don't have like just one processing core that can do this. So I managed to change the program in such way that at the time, all cores of the processor are working on that. So, for example, my laptop, it has 12 cores. So at the same time, each core is working on a different image, and that speeds up the process quite nicely. I think now we are at 20 or 30 minutes per dataset. So that's quite a nice improvement from the 5 hours that Mirek said. It also depends on the computer.
On a laptop. I was just
yes,
about to ask.
It's
is
a laptop.
There needed some supercomputer or anything like that?
I mean, the better computer, the faster it is. So usually, like in laboratories, they have access to better computers, so it can be even faster.
What developments are ahead of you? What do you need to improve, and what are the limits of the method, maybe?
Of course, there is always a lot of things that can be improved in research. In the introduction, we have seen 3 examples. The first example was the perfect crystal. It works even better than the TM. because those tricks behind the scenes that cannot be done in TM. But again, TM has its own advantages. Then we have seen the good crystal. With good crystals, again, we can get even better results than in TM. The last example was average crystal, the crystal that diffracts reasonably, but there is also strong background, strong absorption, and for it's at the edge. But it still can be done with those speed enhancements that were hard-coded by Pavlina to our software. User doesn't see it, but from the practical point of view, it is fast. But there are crystals that are that absorb a lot and diffract just a little. And these are very challenging. In TM, you can still work with them because the electrons are faster and the diffraction is stronger. In SEM, this is a challenge, and this is what we should improve, perhaps even with the help of classical algorithms and even artificial intelligence, to discriminate the noise from the signal that we want to see. So this is one of the challenges. And then, of course, many other things, but I will not go into detail. So this is perhaps the most important thing.
Welcome back to the Unseen Thought podcast, and we were talking about data and about huge amounts of data you need to process and collect. Therefore, you developed two open source tools called STEMDiff and eDiff. What's their purpose?
To explain this, again, we prepared some simplified scheme. The scheme is as follows. In the upper row, we see the crystals as they can be seen with arbitrary detector either in SEM or TM, and in the bottom or in the lower row, we can see their diffraction pattern. So if we have one crystal, we have single diffraction pattern that can be symmetric if the crystal is well aligned, but this is not so important. Let's suppose for the moment that the crystal is well aligned, we have symmetric diffraction pattern with spots. If we have two crystals, we have two diffraction pattern, and so on and so forth. If we have more crystals, the spots starts to be arranged in rings, and if we have powder electron diffraction pattern, so powder, many monocrystalline, nanocrystalline material in the sample, then we have the diffraction ring. And now to your question, what we have developed, the first piece of software, which is called STEMDiff, so scanning transmission electron microscopy converted to diffraction, converts this huge data set to this single powder electron diffraction pattern. So this is the core, and this is the part of the program that Pavlina helped us with very much. The second program is, let's say, quite trivial, and there are other pieces of software. We developed it just to continue in the same line, to have the same software as the user uses to convert this huge data set to a powder diffraction pattern, and this is for the processing of powder diffraction pattern and produce those graphs that we have seen and compare with TM. So the eDiff program is a kind of trivial, but there is a continuation of the STEMDiff. This gives us the final results.
Yeah. And I know you, Paulina, used also some AI tricks within the process. Tell us more, please.
Well, I use it in two areas, let's say. One is that I use AI to actually help me as a programmer, and then I use AI also to do some tasks. For example, to be specific, in this case, I created a neural network that helps us with the noise and background corrupted data. Here is an example of those challenging samples. The first row is a bad sample. I can't tell the name of it, which is correct. Mirek would perhaps help. For me, it's just
magnetic form of iron oxide, magnetite.
Okay.
Yes, and underneath there is even a worse sample. Also, the name is mystery to me.
Lanthanum trifluoride.
Yes,
Oh.
exactly.
Not that
Thank
difficult.
you. Thank you. And in the second column, you actually see how the Well, only the first part.
Okay.
Yes.
Do?
Yeah, the input one. It's like what we get from the microscope. So you
looks like mess.
yes.
Yeah.
Exactly. Noise, mess, that's
Okay.
it. You can't see any diffraction pattern in there. Then next to it, there is the target, which is something that we want. And to get this, I actually had to apply several deterministic operations. It was a combination of morphological operations and so on, to produce it. And it took me a lot of time. And it was not automatic. I had to look at the data to obtain this. And this is something that no one wants to do because it takes a lot of time. And for each sample, you actually need to do it over and over and over again. So I did this for various samples. And that's how I obtained the data that are actually suitable to train a neural network. The problems with this data that Marek already mentioned is the background noise. If you look here, like this is the original input, the profile baseline, in ideal case, should be at 0, which means that there is no background and you can clearly distinguish the peaks. Another problem are the diffraction peaks itself. You need to see them, you need to distinguish them. So in the input data, you perhaps see only the dominant one, but the smaller ones are completely lost in the background and in the noise. And once I got this data, I use it to train a neural network. And the lower row, there is the actual example, the output. So this is, I think, the gold nanoparticles. So this is not the most challenging case, but even here, we can see that there can be an improvement.
This is like a simulation, and this is the real result?
Input data is the original data. Output data is what I got from the network, and the target data is what the quite difficult and tedious workflow that I was doing to get from this.
So as far as I understand it, this is artificial intelligence output and this is the human output.
Yes,
So
yes,
it is
exactly.
quite close.
Yes.
Great job, I guess. Aside from separating signal from noise, where else or what are the typical AI tasks you can use in electron microscopy?
There are quite many. It always depends on the application or samples or whatever you want to do. I would start probably with classification, but actually on this picture I can describe all of the typical tasks. Like in the first image A, you see that there are some cells, but it can be anything. It can be some structures of a material or so. And the classification, basically it tells you which is what. So we see red particles, purple particles, and such, and the classification automatically says which particle is what. Yeah. Then, for example, there is segmentation. It is also important in electron microscopy because it helps you to find boundaries of objects. So then you are capable of doing other analysis. You can do 3D modeling or whatever. Then the restoration and noise reduction that we already talked about, and even detection. You can detect some rare events or, I don't know, or some atypical structures in the data. So no one has to go through one picture by one picture by one picture to do it for you. So this is very beneficial to use AI.
Pavel, what role played the time peaks-based detectors in this research, and what device exactly have you supplied?
Well, we supplied to Institute of Scientific Instruments one of our ePix TimePix 3 detectors, which means that it's not just camera, but it gives you information not only about the electrons in a position manner, but also in a timely manner, which means that you can at the single time detect position of the electron, the time when it occurred, and also the energy that it deposited in your sensor, which means that it's basically a digital detector. So out of the detector you have already the stream of digital data, not as a traditional cameras that are used in electron microscopy, and based on that we able to do like a lot of digital kind of tricks, I would say, to keep it very simple. This illustrates the mode of operation. So really for every single electron we get just the 1 and zeros for that event, more precisely 48 bits per event that you detected on your detector.
And we are getting to the maybe key feature that was used in Mirek's research. What enables us to do the one-spot diffractions?
Again, because you just end up with the stream of electron events, then since it's digital, you can reconstruct any image that you want, basically. So these images are binned based on your dwell time that you're using in your electron microscope. It's synchronized with your electron beam, and based on the information that you're collecting, mainly based on the timestamps, then you create these images. So you can select basically any area on the detector, and in this way create the virtual aperture, and then recalculate the image that was already taken. So you need just one go for this. You collect all the data in once, and then in the post-processing you can do many things. If you're interested in a virtual aperture, virtual segmentation, or then even see the individual diffraction pattern per the spot.
Cool. So it works both ways. I can click either in this image and get the diffraction.
Yes, exactly.
Or click in the diffraction and get the image.
Yeah, and select area on your detector, and then it's the selected area diffraction imaging.
Who could use it again in real life applications?
If we're talking just to the electron microscopy, then basically any user of the SEM, no matter whether it's like material science research or industrial research or industry like semiconductors.
In this case, you've implemented the chip into the Helios G4HP SEM by Thermo Fisher. We have an image here, maybe, and this is not this microscope, because in fact, the detector could be implemented in many different kinds of microscopes, right?
Correct.
In what kinds?
Any microscope that the customers already have, because our detectors is pretty easy. It's easy to mount, and it makes the upgrade of the microscope very feasible and actually really easy. So you can here see this is a test microscope, because we had also the national Toucher grant with them. So within that grant, we implemented our detector into the test microscope, for example. So they are almost fully integrated into the existing microscopes.
So let's imagine the situation, the story. I am a researcher, as Mirek, for example. I have my microscope, my SEM microscope, for several years in my laboratory, and I want this upgrade. What I have to do?
Just call us.
Okay, and how much and how long?
Well, it can be relatively simple. So within a few months, then you can get your upgrade on your existing microscope.
Pavel, Mirek, Pavlina, you are collaborating within a project of Toucher, the technology agency of Czech Republic. Are there any other projects ahead or running, and what do you want to achieve in these projects?
Maybe step by step answer to your question. So other projects, it was in fact a series of projects from Technology Agency of the Czech Republic. In the current one, we would like to finish our software so that it was even more user-friendly and that it worked even for more difficult samples. And for the other projects, we have submitted a proposal to Czech Science Foundation and also some artificial intelligence program offered by Technology Agency of the Czech Republic. We would like to go even beyond the limits of current software, enhance it so that it could be used also for monocrystalline samples in a similar simple way. So that's it.
How important is for a company, commercial company, to collaborate with institutes and academia on these projects?
For us, it's a very valuable collaboration, because you get the insight from the end customers as well. So, and this gives us a lot of information how our products should evolve for them. So we always favorable for any such a kind of collaboration because it gives us a lot of information.
I guess you got some feedback during the process. Do you remember any feedback that they forced you to redo something in deep? What was the I don't know how to say biggest mistake you made, and the feedback helped to repair it?
Well, as I would say with anything, so it's a question of hardware and software, and typically you have like some bugs in software, so this feedback is used to correct the software, the bugs in the software that you have, not so much in a hardware way, because this is something that's said and done, but as I was referring before, that we just streaming this just stream of electrons, stream of 1 and 0s, and there's a lot of processing that has to happen to provide such an image.
I guess we are walking on the edge. It's cutting edge technology, so the bugs or mistakes are part of the story, right?
That's correct. Of course, our customers don't want to see them, but
yeah.
we
But
do our best.
we can fix them. Anyway.
Yeah. I think like we had only a problem that our computer was too fast for the program, and we just called you, and I didn't understand really how it was happening, but you fixed it immediately, so that was great.
That's important. Mirek, how do you see electron microscopy in 10 years? Regarding, we are talking about improvements. So in 10 years, what is your vision?
A simple question is I do not know. But I think that there are two extreme cases that may happen. The first is let's call it pessimistic, that the microscopes will be more or less the same as they are now. So quite modern machines with new detectors, more and more possibilities, but basically the same. The second vision, let's call it optimistic, or I don't know if it is so optimistic, is that it will be a machine that you just enter the room and you will talk to it, and there will be some artificial intelligence, and you will say, do me electron diffraction pattern from this area of the image. You point with your eyes, the artificial intelligence will somehow read what you are looking at, and will make you an electron diffractogram. So I mean, in 10 years, who knows what the future will bring.
Okay. Do you both have any ideas?
Well, I don't know. Perhaps I think that now the problem with artificial intelligence is that it does something. Well, usually it does what you want, or at least it looks like it's doing what you want. But in the end, it does not really understand it. It is able to learn patterns in your data, but it can't interpret them or tell you, I'm not really sure if it's true. It just says that it's true. So perhaps this will get better, because now it depends on the data that you feed it during the training process. So the results are only as good as the data is. So I would say that currently AI is a great assistant. It is faster than me when I want to, I don't know, like look up something or things, but it does not bring the innovation itself, or it does not yet replace the science work on its own.
Yeah, thank you. What about you, Pavel? Your future?
It's always difficult to predict, right? But if you look at the current developments, electron microscopy, then hardware-wise, it's more or less the same, except the detection technology. You can, because just to be able to visualize every single electron, this is basically perfect, right? It cannot be any better. But the pressure is always to get more data, faster and better data. And then there's, of course, this software development, as Mirek said. You can just enter the room, or just have the prompt on a microscope as a ChatGPT, and just tell them what you want to do. The question, I agree with Pavlina, is whether it will give you some reliable data or not, or you will have to still need to use your human intelligence to it. So mainly on I see the development mainly on the software side.
Well, thank you. I wish you good luck in your research and business as well. And thank you also for listening to the podcast till the very end. And please stay tuned for more success stories with a bite of Advacam and Advascope inside.
Unseen Talks are brought to you by Advacam, a world-leading producer of single-photon imaging and particle tracking cameras. We're imaging the unseen.